So the very first example I want to do is a non-uniform charge distribution because based on office hours, some people have trouble with it. So I'll start with this example here: a sphere with non-uniform charge distribution. Here it is. This is the sphere. The radius is capital R, and the charge density within the sphere is B times R squared. B is a constant, but notice little r is not a constant. Little r is a distance from the center.
Is it true for all spheres that the charge distribution isn't uniform, or is that just a specific case?
Just for this, we could have uniform. So the question is, find the electric field inside the sphere and outside of the sphere. What we expect is that the electric field outside of the sphere will act as if it's a point charge, but within the sphere, it's different. So let's start with inside the sphere, R less than capital R. In that case, we apply which concept?
Gauss's law.
Gauss's law. Choose a Gaussian surface here, right, within the sphere of radius little r. And then we choose a sphere because of spherical symmetry, right? Although the charge distribution is not uniform, it is still spherically symmetric. So we have E dot dA, closed surface integral, is equal to the charge enclosed over epsilon naught. We have done this many times. The electric field is radially outward, and the area is radially outward, so the dot product becomes E dot dA, and then becomes EA, and the surface area of the sphere of radius r is 4 pi r squared. It becomes E times 4 pi times r squared. Here I have 1 over epsilon naught. Now normally, if the charge distribution were uniform, then you say rho times the volume. It's not uniform. So we have to turn it into an integral. It's going to be the charge density times dV. The integral will go from 0 to little r. And this is little r. So we get E times 4 pi r squared equals, and this one here, yeah, equals 1 over epsilon naught. B times R. From 0 to what? To what point?
Little r.
Little r. The 4 pi cancels. And we get E times R squared is equal to 1 over, equal to B over epsilon naught. Now, R squared times R squared is R to the 4th. When you integrate, you get R to the 5th. Both sides. And finally, then E equal to B over 5 epsilon naught. R to the 3rd power, right? And make a vector.
Will you ask us to find B for most of these problems?
B.
To find B? Yeah.
I have to give you more information in order to find it.
What would we need?
For example, I can say the total charge is Q,
Okay.
and you can find.
I see.
Yeah. Yes.
Oh, no, because we're looking at the spherical shell.
Oh, yeah.
No, no question.
Yeah.
So that's the electric field inside the sphere. Outside, for R greater than re capital R, everything is going to be the same. You get Gauss's law. Now, the Gaussian surface, which I forgot to draw, needs to be here now, right? That's the Gaussian, this is the new Gaussian surface for this part. No, you have a question?
Then I just have a conceptual issue that I think we can point out.
You can ask.
Well, I feel like our chair is expanding, but the 4/3 power cube would be our volume of a,
For a solid
for a
sphere.
solid sphere, right?
Yeah.
But then, because it's a thickness dr,
Mhm.
that whole integral thing goes, that 3 goes away, the
This
4.
becomes
right,
right,
okay.
dr. It's a spherical shell, radius r and thickness dr.
Thank you.
So on the left side, we still have what we had earlier. It's going to be E times 4 pi r squared. Here we have 1 over epsilon naught. We would have this. But what are the bounds of our integration now?
0 to big R?
0 to big R. Why not 2 little r?
Because there's no charge.
Good. So your integral should go from 0 to big R, because outside here there is no charge. 0. So get that. So you have, again, this 4 pi gets cancelled. We get E times R squared. B times capital R to the 5th over 5 epsilon naught. So we get the electric field to be B times R to the 5th over 5 epsilon naught times 1 over R squared. And of course, you can make it into a vector, because of symmetry, we already knew the direction. We figured the direction first, radial direction. So that's the electric field. And we predicted that it would be 1 over R squared, right? Like a point charge when you're outside. So that's done. Let me do one more question. Like that.
So for these two examples you just did, so you did for r is less than or equal to r,
Yes.
and then for r is greater than or equal to r.
Yes.
So if it's equal, which equation?
They would match,
They match, okay.
right? You plug in, it would be capital R to the 3rd power. And here we have R to the 5th, R to the 2nd, it would become,
Okay, so yeah, okay,
Yeah.
I see, thank you.
they match, it's continuous. Yeah. So, the next, yes,
Oh, actually.
are you sure?
Yeah.
So the next one is, I have 2 more in mind, and I get yours.
Oh, and then could you also do one with uniform?
With uniform, then it will just be rho times volume.
Oh, okay.
Yeah.
Okay. So just,
So we get, the next example. Yeah, I remember. So here's the next example. Sometimes we keep doing Gauss's law, and we forget Coulomb's law completely. So here is the x-axis. That's the x-axis. Imagine we have a rod. Sorry. This is 0. And this is L. Yeah, let me just do that one and minus that. Okay. Minus L, yeah. Let's say the charge density here is lambda. The charge density, linear charge density is lambda. Alright, the linear charge density is lambda. Yes,
So is the charge a weight here, when you say the density is, like, you said density, right, charge density?
Yeah.
Is that a weight here?
it's charge per unit of length.
Um,
It's density in the sense, how packed is the charge?
Oh, okay.
Yeah. So, we want to figure out what's the electric field due to this rod at this point. What's the electric field at this point here? Suppose this point is located at a distance d. Now, if we had a point charge, it would have been Q over 4 pi epsilon naught times 1 over r squared, right? But this one is not a point charge, it's spread. So what's the approach?
We can look at a segment of the rod.
Segment of the rod, slice the rod into little slices. So here's a small slice. Small slice, and here, this is the back. So what would this distance be?
Yeah, sure. Oh, wait, no, sorry. It's, d minus x, yeah.
D minus x. So here's what we know that DE, 4-point charge is going to be dq over 4 pi epsilon naught times 1 over r squared times r hat, right? That's dq. What's dq? In terms of lambda.
It's,
Lambda dx.
Lambda dx. Now, what is r? It's the distance from where to where?
The charge to the point,
From the charge to the point. How much is that? Or what is that?
d minus x.
D minus x. So d minus x squared. Right? R squared. What is r hat? It's a unit vector that points from where to where?
The segment to the points,
From the
Charge.
no,
from the
point
charge
to the.
to the point where you want to find the electric field. The charge is here, the point is there, so what's this direction?
I have.
I have. So that's the. That's it. I'm going to drop the vector signs, because it's just a one-dimensional problem. It's understood, it's in the x direction. So I just put E. So E is simply going to be lambda over 4 pi epsilon naught. Times 1 over D minus x squared. Integral from where to where?
Charge to the point.
negative L to L.
Yes, the whole segment from minus L to L. Good. Lambda over 4 pi epsilon naught times, what's this integral? Yes,
What's the integral with respect to? Is it?
oh,
Yeah.
I forget the x, sorry.
No.
So now what's this integral?
Integration of work.
That is
Okay.
Maybe that'd be squared. This is just a.
It could be negative 1 over d minus x.
okay. So 1 over d. I'm saying there should be a minus.
But where did the 2 go?
What?
Then when you do a use of it, d minus x goes to negative 2x, right?
No, you're doing it, it's the integrand, not the derivative.
Oh.
Right, it becomes actually 1 over d minus x Because if you differentiate this, the chain, when you do one over something, it becomes to the negative second power, and then a minus one comes out. But by the chain rule, you get an additional minus one, so this is fine. So do it slowly on your own, and you'll get it. Evaluate between minus tau, P capital F. And, yeah.
So, because two comes down to equal 8 times PQ.
You mean,
When you differentiate.
uh-huh.
Oh, never mind.
It's okay. So, evaluate that, you get, oh, there's no reason to evaluate it, I'll just leave it. You can evaluate it on your own. My objective was, how do you set up the problem? I remember you have a question, so I'll get to it. Yeah,
Okay.
and, I have one more for you. We did non-unit, we did some coupon. But forces, let's do a quick one. For forces. So imagine I have positive lambda. And this one here is negative lambda. Their length is L. The length is L. I have two line segments, one of them is positive lambda, the other one is negative lambda. So they would attract or repel. They would attract, right, because they're opposite each other. I know that L is not infinite, right? But let's assume L is large enough that we can use the result for infinite charge density, for an infinite line. What was the electric field for an infinite line? If lambda and your distance r away, you have to look it up. Maybe. Lambda over what?
2 pi
2 pi
r
epsilon naught r,
hat.
right? Times r hat, yeah, that's I would just use the magnet. That's correct. So, yeah, so that's the electric field for an infinite line. Suppose these guys here are, these two lines are a distance d apart. Distance d. What's the force between these two lines? And I want what's the force? Yeah, what is the force between these two? What's the force that, let's say, line 1 exerts on line 2, or line 2 exerts on line 1? By Newton's third law, they would be the same. So what's the total force that this line exerts on this?
0?
Why would it? No,
You said it had the exert on each other, so it canceled out.
no, I mean, that's Newton's third law, right? I push this desk, it pushes back on me, but my force is on the desk, and the desk's force is on me. So that there isn't that force on the desk. Yeah. So there is a force on this line.
Is it positive Q over L times that, the E?
Okay. So I like that. So let's imagine, let's say we want to find the force that the positive line exerts on the negative line, right? Let's take a little segment here. There'll be a little dq here, right? There'll be a little dq there. And it will experience a force this way, right? It will experience a force in that direction. So what would the force be in terms of the electric field? dq times the electric field, excellent. dq, whatever dq is, times the electric field, right? dq times lambda over two pi epsilon naught times d, right?
Why is the force that way again?
The positive will attract the negative. Yeah, it's an attractive force. So, we get, then, sorry, I should not have called it F. I should have called it DF, because it's a small force. DF, sorry. That's the force on just that little piece. So the total force would be an integral, right? But notice lambda is a constant, 2 pi, epsilon naught, and d, they're all constants. So it just becomes lambda over 2 pi epsilon naught d integral dq. This becomes lambda over 2 pi epsilon naught d times the total charge, right? Total q is q. What is q?
Lambda times L.
The total, yeah, charge density times the total length. Lambda times L, or negative lambda times L. I just want the magnitude of the force. The direction we already determined, I just want the magnitude. Oh, that's the answer. Yeah. Repeat that.
If we were to just have plugged in, for like F equals QE, and we were to just assume that, well, Q equals lambda times L, why can't we directly
We
do
could
that?
have done that, but we have to realize that this part is a constant. If that weren't constant, then you wouldn't be able to do that.
Okay,
Yeah.
I see.
And then so that's a total force between those two charge lines, right?
Yes.
Then, sorry, when would that not be a constant?
The,
Yeah, would it be if there was like a
let's say,
third?
I have a line with a sphere or something.
Okay,
like that.
okay. Okay,
It's not equidistant.